Today I'll be talking about PolkaVM, a fast and secure RISC-V based virtual machine. A little bit about myself. As mentioned, I'm an engineer at Parity Technologies. I did a lot of coding for Polkadot. More recently, I haven't been coding as much. I've been doing a lot more presentations and teaching and stuff. But something that hasn't changed is I'm a full-time student all the time. So I'm constantly learning about all these new technologies, and I know that RISC-V is kind of a very hot topic, and so I want to make sure to present some of the things that we've been doing and learning about. I want to admit I am an imposter here on this stage. I am not a VM expert, but I do have a lot of friends that I'm very fortunate to be able to call VM experts, like Gav, Sergey, Jan. They built EVM, WASME, and PolkaVM. And I ask a million questions and they give me answers. And so this isn't the kind of collection of information I've gotten from them. And I wanted to present with you that information, take you along our journey. So basically, I hope to distill kind of the knowledge we've gained over time. So at Parity, we built a lot of blockchains. We've gone through using the EVM, using WASM, using RISC-V. So I want to tell you a little bit about our journey, what we've learned. I want to describe PolkaVM and how we use it, and then convince you, hopefully, that PolkaVM would be a great addition to any modern protocol. First, before we even get started, what do we look for in a virtual machine, right? So we're building virtual machines for blockchains. I think one of the first things we think about is we need a deterministic virtual machine, something that, of course, you're running all these nodes around the world. They all need to come to the same, with the same input, same output, right? They can all come to consensus. They also need to be sandboxed. We don't assume, for example, actors deploying stuff into this virtual machine environment are good actors, right? So if they put some malicious code, we want to make sure that the VM is sandboxed so that it doesn't affect other applications or the actual nodes that are running these applications. Of course, it needs to be metered. This has to do with like block limits and gas payments and all that kind of stuff. We want to make sure that people, when they're actually using the execution, are paying for what they actually use. They're not getting free compute. And then finally, or the last two, general purpose and developer friendliness. Depending on which VM you use, you kind of get a sliding scale of this, right? So not all VMs are as general purpose as others. Not all VMs are as developer friendly as others. But I think as a high level goal, when we look for a VM, we want things that are as general purpose as possible, as easy to run any kind of computation as you can, right? And developer friendliness as well. Like we want to be able to use the tools and the languages and libraries that you want to use, right, in the VM environment. So these are kind of like high level goals. So with this in mind, let's talk about the EVM, right? I think the EVM was a great decision and a great product at the original time of building Ethereum, right? So I think the key principle of the EVM was to keep it simple design, keep it simple to implement, right? There was a yellow paper which designed the full, or which described the full specification for how you could build a syncing Ethereum client. And in that yellow paper was an exact design for this VM, right? So it had to be simple enough that anyone could actually understand and implement this code, right? And this kind of first mover advantage of using the EVM in Ethereum, the first kind of programmable blockchain, allowed it to get a lot of, the head start in kind of the blockchain space. Like all the big DeFi protocols, all that stuff is built using the EVM in mind, right? And there's billions of dollars already being secured by the EVM in production. So it's a really, again, simple, secure, working VM. But unfortunately, it made a few quite bad decisions, which kind of affect the performance of the VM itself, right? So first, using 256-bit registers, right? Your actual hardware is using probably 64-bit registers, right? So this is make it slower. It uses big endian, whereas again, most hardware today uses little endian. So there's all this conversion that's happening. It's not designed for native compilation, so it's basically an interpreter, right? So it's again running slower, and it has inefficient gas metering, right? So of course it is secure, it has good gas metering, but it's not done efficiently. And of course, the EVM introduced a whole new VM environment, a whole new set of instructions. Therefore, it basically had to build a whole new developer ecosystem, new languages, new tooling, etc. Right? I think we're in a spot today where we can say EVM was really good for what it was designed for at the beginning, but probably not the right choice for modern blockchain platforms moving forward, right? And so this is the same thing that we had. We had this feeling almost 6 years ago that the EVM is probably not the way forward for modern blockchain systems. And so we should look at other alternatives. We should learn from what we want and see if there's better choices. And at the time, the best bet on the next generation blockchain VM was WASM, WebAssembly. And this, again, checks all the boxes we expected and looked for in a VM, right? Deterministic, sandbox, metered, etc. It's extremely well adopted by big companies like Google, Microsoft, Mozilla, so they're maintaining it, they're making sure that things are working well. It supports all major programming languages, and it's designed to execute at near native speeds. So this sounds really, really great. And we were also thinking, okay, beyond just smart contracts, we were also thinking about using WASM for the actual blockchain execution, for this thing called the blockchain runtime. So in Polkadot, we were trying to design this verifiable rollups and this verifiable light clients, right? And to do that, we wanted to base everything off of an execution meta protocol. The idea being, if you built your blockchain and your core blockchain logic was written in WASM, then we could, by having an execution meta protocol, we understand WASM, we can execute your blockchain and secure it. We could basically create a secure rollup using that kind of standard platform. And so this worked pretty well. We also have the ability to do forkless upgrades if we were able to put this WASM on the blockchain and then upgrade that storage. We can upgrade the blockchain logic as well. So that was something that's really exciting. And building logic for the blockchain is very similar. The needs are very similar to building for a smart contract. The only difference really is that the blockchain core runtime has like lower level access to things like the blockchain state and like parts of the blockchain. So it's just a much more powerful logic. But the needs of it being sandboxed and of metered and deterministic, it's all the same, right? And of course, EVM wouldn't work for this. EVM was not designed for this kind of scenario, for building, a blockchain runtime. So it wasn't really a choice at the time. But the reality was, when we actually went and used WebAssembly, it was really good for the blockchain runtime, really good for that situation. But it actually turned out to be a suboptimal choice for smart contracts. I'll go over this. So the fastest VM for WASM is WASM time. This is like a streaming compiler. Which is executing really, really fast, only about 2 times slower than native speeds, which is quite fast. But the problem is that it itself has nonlinear compilation times, which can lead to compilation bombs. So if you're building a blockchain runtime, this is not a big issue because we could have our own kind of validation. The amount of people building blockchain runtimes is much smaller. It's not a big problem. But if you're building smart contracts, this becomes a problem because if anyone can upload a WASM blob that has some kind of compiler bomb in it, that can be really bad for the performance of your blockchain, right? So we actually had to execute WASM smart contracts in WASMI, which is an interpreted VM. And this is way slower, 20 times slower than WASM time, which is already 2 times slower than the native compilation, right? So much slower. We also realized that WASM blobs are quite big. So that, compared to ERC20 in Ethereum, the WASM equivalent would be about 10 times larger. So that's a much bigger blob. Again, that affects network speeds. And also the WASM bytecode couldn't easily be Merkleized. So if I'm trying to prove the execution of one specific function inside of a contract, I couldn't just take that, like a Merkleized proof of that part of the smart contract. I'd have to upload the whole blob. And that, again, takes a lot of, because the blobs are big, it takes a lot of networking bandwidth. And then we also found that WASM, again, being supported by all these big companies was kind of a blessing and a curse in the sense that WASM itself was also being iterated, it was also growing. So the initial MVP of the WASM instruction set was 170 instructions. Now today it's about 220. At some point we had some breaking issues where they introduced new standard instructions. People were using our VMs for other projects, and then their stuff wasn't working. So we had to go and update and maintain our VM, even though we weren't using these new instructions. So again, the fact that WASM was kind of growing was a problem in using WebAssembly. So again, we found something that was better than EVM, but still not great in all the ways. So we kept looking and kept investigating what are the other options available today. So we left no stone unturned. We had Sergey looking into the ePBF ISA, which was used by Solana, and it wasn't enough better than WASM. It was okay in some ways. It was kind of simpler, but it wasn't enough better. Jan actually started looking into RISC-V, and he implemented the first prototype of the VM in 1 day. So that kind of shows how simple RISC-V is as an instruction set, right? And he was able to even build a recompiler in 2 days. And that 3-day project was outperforming production level VMs. So we can see here on this graph, this is running an NES emulator that he also wrote in different VMs. And this 3-day RISC-V project was outperforming WASMI by 4 times, and even things like RPBF used in Solana by more than 40 times or whatever, right? So this was very, very promising. RISC-V seemed to be really fast, really simple. And has a lot going for it, right? RISC-V is small and stable. So the baseline specification is only 47 instructions. Again, go back to WASM was 220. This RISC-V architecture was only 47 instructions. The instruction set is totally free and open source, so anyone can use it without any license fees. It's modular and extensible, so you can basically use this base level instruction set and then add these different extensions to the instructions if you want to add different features and functionalities of your VM. Many of these things we don't use actually. In a blockchain, we don't use floating point numbers, we don't use atomics. So the ability for us to not include those extensions was great, right? It's efficient and scalable, so designed for using for low power computers or supercomputers. And of course, well supported. So, RISC-C already supports it, LLVM already supports it, and it's, again, RISC-V is picking up a lot of steam in the industry. So RISC-V has a lot going for it and being a good, as a good VM environment. And thus, PolkaVM was born. So what is PolkaVM? So PolkaVM is a RISC-V based virtual machine, and I'll talk about that in the next slide. It uses 64-bit registers, 4 kilobyte page, 32-bit address spaces. So this is exactly the same kind of default options that your operating systems use today. Not like Ethereum, which uses 56-bit registers, and you have to do all of this, 256 math on a 64-bit computer. This is using the same kind of expectations as your normal operating system, right? It uses a Harvard architecture, meaning that you don't have problems with self-modifying code or being able to overwrite code in memory. This again eliminates a lot of problems. It's good for blockchain. It's guaranteed linear time recompilation, right? This is really important. So we can recompile this PolkaVM stuff, this RISC-V based stuff, into your native code at linear time. It is guaranteed to be 100% deterministic, and it's very fast and efficient in gas metering. So our gas metering, when we turn it on, only adds about 10% overhead to the execution time. Very, very fast. Now, I want to mention here, PolkaVM is RISC-V based. It is not exactly RISC-V. So we design it in a way that you can access all the main RISC-V tooling, things like LLVM, GCC, Rust toolchain, etc. But we then eliminate from the ISA all the useless instructions. Any things that don't make sense for a blockchain VM, that only make sense for like a physical chip, we eliminate those things, right? And then we also allow in our version of PolkaVM variable instruction length. So this allows us to take certain kinds of instructions that would take multiple, or operations that would take multiple instructions to be only taking one instruction because they have variable length instruction set. And then we also introduce a custom binary format, right? So we tried to do this custom binary format, which removes a lot of the complexity of compiling the code off the chain, so that on chain we get really fast JIT compilation and reduced binary size. And so really PolkaVM is not RISC-V, but it's what you would build if you took the RISC-V ISA and said, I'm not building a physical chip, I'm building a blockchain VM. And that is what PolkaVM is. It is inspired by RISC-V, but does the things that make sense for a blockchain VM. So it's very fast. I'm going to show you some graphs. So PolkaVM, in a one-shot execution time, that is basically being like including compilation, initialization, and executing of the code, it is faster than even WASM time. It is right up to there with native speeds. And again, I want to show you here much faster than Solana RBBF, much faster than WASM we were using before. And I have here a CKB VM. This is a pure RISC-V VM. So I want to show you that the ideas kind of introduced in slightly modifying the RISC-V ISA has achieved much faster speeds than actually implementing the RISC-V ISA directly, right? That's what this last VM is here. So very fast. If we look at the execution time alone, it is a little bit slower than WASM time, but come on, it's pretty good, right? Like compared to especially to Solana, WASM, CKB VM, right? And finally, the compilation time. So this is a log scale. The compilation time, this is why it's better than WASM time in this context. That PolkaVM is just a little bit slower in execution, but is much faster and much more predictable in compilation time. So when we actually compile the PolkaVM blob into your native code to actually execute it, we get super fast compilation speeds. And again, this is about 40 times faster than Solana or WASM, and about 400 times faster than WASM time. So even though WASM time is a little bit faster, it's 400 times slower and unpredictable in terms of compilation. So this makes PolkaVM a really great choice for a blockchain VM. And again, you see that it's fast, and the reason why it was always designed for speed. So one of the things we did with PolkaVM is, since we control the specification, as the developer Jan was building this VM, he was also updating the spec. If there was something that he could do to design the VM to make it faster, he wasn't forced or held down by a specification written by someone else. He was able to update the specification for PolkaVM to be able to actually make those faster changes a part of the implementation itself, right? And again, because PolkaVM has made many decisions, keeping it close to modern architecture, like 64-bit registers, a 32-bit memory size, whatever, the instructions coming from PolkaVM are mostly one-to-one to what you expect to run on native, right? So it makes that compilation to native very fast and efficient. Finally, we moved a lot of the off-chain, a lot of the complexity of compilation off-chain. That's what this diagram is showing you here. So I mentioned this custom PolkaVM binary, which comes from a special PolkaVM linker recompiler, which takes in our standard ELF file from toolchains, right? And so this custom PolkaVM binary has a bunch of optimizations, things in it like this, variable length instruction set, and and all the other things, to be able to basically get a binary that runs and compiles very quickly to native when you actually get to PolkaVM. So all of this complexity of doing the linking and recompilation happens before you actually upload the blob to the blockchain. And then beyond the technicals, I mean, wow, this is fast, right? But PolkaVM actually introduces a bunch of new ideas which make it kind of a very exciting thing for a blockchain VM. And I'm going to go over these bullet points one by one. First is we support Solidity. So we have this thing called the Revive compiler, which is a Solidity compiler for PolkaVM. We know that the majority of blockchain ecosystem depends on Solidity contracts written for the EVM, right? So we built the Revive compiler, which can allow us to take most Solidity contracts and turn them to something that's PolkaVM compatible, right? So basically, Solidity can be compiled to Yule, which is the intermediate representation for the EVM. Then that can be converted to an LLVM IR, right? And that LLVM compiler can then target RISC-V, which then supports PolkaVM. So basically, most of your Solidity smart contracts can be run on the PolkaVM, which is very exciting, right? And we hope this will help bootstrap the adoption of PolkaVM. PolkaVM also has the idea of continuations. So continuations are like game save state. So again, if you imagine you're playing a game emulator, and right before a boss, you do a save state, right? You play the boss, you lose, you start the save state over, you're back at where you started on the program. Imagine here, you're running a program on a blockchain, but that program takes more than one block to execute. You can start the execution of the program. When the block limit runs out, you can then take all of the stack, the registers, the memory, store it in a DA layer, right? Some non-persistent storage. Then the next block starts, you can take that stuff from the DA and start re-executing your program right where you left off. You're actually able to emulate large running programs over multiple blocks using the features of PolkaVM. And this is because we have a addressable stack. And because of this, we're also able to run things like Doom and Quake on chain. So we have this thing called CoreVM. CoreVM is basically like a Docker for PolkaVM. Inside of this Docker, you can basically run mostly unmodified native applications. We're talking about x86, x64, ARM64 programs. You can directly run them on PolkaVM inside the CoreVM. You get 100% determinism, reproducibility inside of it. You get video and audio outputs. You get read-write access to a virtual file system, and many more. Like the idea is that you could build drivers targeting CoreVM, allowing you to run basic applications on your blockchain. Now, I'm not saying that you should run Doom on a blockchain. I'm not sure that makes a lot of sense. But the point is it's showing that you can really take any kind of native executable and run it on top of PolkaVM around our CoreVM wrapper and run that on a blockchain. Applications, they just think they're running on a normal computer, right? They don't even know they're running on a blockchain. And finally, the PolkaVM has a formal specification. Again, this is something we learned that was super important from the EVM world, right? The Ethereum world. That we made PolkaVM simple enough and understandable enough that we actually formally specified it so that anyone can go and implement it themselves, right? So we have over 41 implementations of PolkaVM already across 14 different languages like C++, Rust, Scala, Java, etc., right? Now, PolkaVM, so the one thing I've kind of been brushing over is that the actual specification is called the PVM. PolkaVM is one implementation, the one I'm presenting so far, that's built in Rust. And it's kind of the de facto implementation. It's the fastest one. It's the one that's basically maintained and is updating with the specification, right? But PolkaVM, the one written in Rust, is also licensed very permissively. MIT or Apache 2, however you want to use it, you can use it in your projects, no problem. Or if you want to build it again, build it from scratch. You can use the specification, build it on your own. Now, there's some downsides. Not a lot, but I asked, of course, we need to show downsides. Downsides of PolkaVM, basically the program blobs are a little bit bigger, about 4 times on average the size of an EVM contract. Okay. RISC-V is not the EVM, so I talked about some of the Solidity compatibility, but the fact is that these VMs are different, right? So there's only partial compatibility. There's probably some Solidity contracts that don't work or that use things that are kind of not compatible, right? And PolkaVM is still relatively immature, right? So it's only started about 2 years ago. There's hopefully going to be a 1.0 soon, but I'm presenting something that's still very rough. You can expect that there'll probably be changes and things that we learn about PolkaVM over the next years. But again, the benchmarks and the output is really exciting here. I hope that it kind of convinces you that it's an investment worth making. Now, a question, should Ethereum use PolkaVM? I think that's the thing. So why am I even asking this? Well, obviously, you must have heard about Vitalik recently proposing that, we could potentially switch the VM engine in Ethereum from EVM to RISC-V, right? Now, kind of a summarized opinion, I don't want to go too deep into this stuff, but the idea is that if we want to plan to scale Ethereum with zero-knowledge rollups, the best choice is actually to use a ZK-specific VM. I don't think using RISC-V is the right choice. If you're going to be using ZK stuff, you should use a ZK-focused VM. But the downside of that, of course, is if you're using a very specialized VM, you get the same problem we described at the beginning. It's not developer friendly. You have to build a whole new ecosystem tooling around that specialized VM, right? We personally don't like the idea of doing that. We like the idea of using a fast general purpose virtual machine environment. But in that case, we recommend don't use the RISC-V ISA directly. Like we just showed you, the RISC-V ISA directly doesn't make sense. It's made for real chips. Instead, you can make some changes, like what we did with PolkaVM, and actually get much better on-chain blockchain VM performance, right? And instead of actually using a ZK for scaling, you could use things like economic security and proactive block validation. And you can also get basically measurably more efficient scaling in this way. Now, I won't talk too much more about this. I have some links, and I'll have the link to the presentation later. But if you want to learn about alternatives to ZK scaling, we have some ideas as well. How will we use PolkaVM? So that's the last piece. So I want to kind of show you how we're thinking about it beyond the normal blockchain context. Well, first, we are trying to recreate a high-performance smart contract platform, a modern one, right? So we will use PolkaVM at the center of a traditional smart contract platform. Fast and linear compilation times means that JIT compilation for contracts is great. You're going to get very fast, high-speed contracts. This leads to more faster execution speeds, which leads to higher gas limits, which leads to higher limits per block, which leads to lower transaction fees. Overall, everything will just be faster. We're using a modern VM, right? We'll get things like Solidity compatibility, but also get things like Rust, C++, TypeScript, all the modern languages supporting this environment. And of course, we are hoping to make an environment which is fully Ethereum integrated, right? All the RPCs, cryptography, precompiles, we can hide all the stuff and basically say, hey, this looks like Ethereum, but underneath it is running a modern VM environment, right? We hope to truly provide a seamless Ethereum-like experience. And then we hope that, if you're trying to build something similar, you could do the same. And then beyond that, beyond the normal smart contract system, we want to try to build a truly decentralized world computer, right? So one of the big takeaways I've had from this is that if you're just trying to replace, a VM with another VM inside of a blockchain system, you have some ledger, the ledger takes some input into a black box, does some computation, outputs back to the ledger. Kind of doesn't really matter what VM you use. I mean, obviously there's speed and there's developer friendliness, but all the VMs are treated the same. But if you create a VM which has features like continuations, like the core VM being able to run applications, right? If you then design a blockchain protocol which takes advantage of those features in the protocol itself, it's not just treating it like a normal black box, but actually knows, hey, it can do things like continuations, then you can actually design something beyond what normal blockchains are able to do today. You can build things like a real decentralized world computer, where at the center of that computer is a decentralized CPU, which is PolkaVM, which has decentralized permanent storage using a blockchain Merkleized blockchain state, which has decentralized memory using an accessible data availability layer, right? It has its own kernel, like using something like Jam, an operating system like CoreVM, right? And security and scalability like a consensus protocol, right? So we actually have the ideas of being able to build real decentralized computers, not just blockchains, not just decentralized ledgers, using technologies like PolkaVM, taking advantage of the properties it has and deeply integrating it into the protocol itself. And with that, we can achieve a lot of things that don't even resemble blockchain and smart contracts today. I mean, if we remember the history of what we're trying to build in this space was this centralized world computer, right? I think that we're kind of get caught up in this feeling of building another blockchain. We realize that blockchain is not actually a good representation of a computer, right? Being able to have, or being forced to be able to build contracts within certain limits of a block, or what you can actually do in that block, is not going to actually create the best outcome. So what can we actually do building a world computer? What can we actually do building a VM which has these kinds of ideas in mind? I think we can do a lot more. I won't go too much into this. If you want to learn more, I think Gav will have a presentation tomorrow at the end of the day, like 4:30 on Jam, and he'll explain the basis of the world computer. So yeah, I just want to leave you all here with these different ideas, and I wonder how you might be able to use PolkaVM as well in your projects. If you want a QR code to this presentation, you can take a picture here. This is the whole presentation. I have a lot of links and stuff. And if we have time, I'll take a few questions. Yeah. Yeah, of course.
Yes, thank you so much, Sean. So we've got plenty of questions, but let's start.
By the way, again, I'm an imposter here, right? So I'm not a VM expert, but I hope they'll answer most of your questions.
All right. So the first one, can modern compiler toolchains like LLVM be trusted to compile smart contracts and runtimes?
I would hope so. I think that would be the case. I mean, I think we'd have bigger problems at a macro level if that wasn't the case. But again, the big problem here is that, for example, Solidity compatibility. It's very fair to say that if you write some Solidity code, you expect it to target the EVM, and you're targeting this PolkaVM. There could be situations where you're not going to get the expected outcome. So it's a little bit questionable there. But if you're building a brand new application and targeting PolkaVM, I think it should be fine. I think using things like LLVM should be fine as well.
Thank you. The next one would be, can you use RISC-V to get ZK proofs?
So yeah, so I think, as I understand, RISC-V is a ZK extension on top of a RISC-V VM. So I believe you could build the same kind of extension on top of PolkaVM. But again, I don't know exactly if RISC-V uses the exact ISA or uses a modified ISA like we do. But my recommendation to the ecosystem, if you're going to use RISC-V as a basis, don't use the default ISA. Don't use this hardware-built or hardware-designed ISA. Use something like PolkaVM, which makes some modifications, which achieves major benefits for blockchain VMs, right? And if you're going to be able to build a ZK extension on top of that, using something like PolkaVM as a baseline RISC-V-like engine would be the right way to start.
All right. Thank you so much. Let's have one more question. I'm
Sure.
sorry, then we're running out of time.
No.
All right. So, one sec. How hard would it be to use existing RISC-V ZK VMs like Risco and Succinet to generate ZK proofs of PolkaVM execution?
Yeah, so man, I wish I knew more about exactly that. I think my understanding is this again, that at somewhere a RISC-V is an ISA. It has a bunch of instructions in it, right? PolkaVM is a modified ISA, which is trying to basically optimize what will we design an ISA to look like for a blockchain VM. Again, remember, RISC-V is literally made for building physical computer chips, right? So whatever we could do with RISC-V, my understanding is we could basically do the same things with PolkaVM if you built those extensions on top of it, right? And you will get all the performance benefits, again, within a VM environment with running on the blockchain that we achieved with PolkaVM, because we do things like this, again, this modified instruction set and the smaller binary size, like doing the off-chain compilation. So it should be possible, but I do not know enough about the ZK extensions to really be able to say exactly what that looks like.
All right. Thank you
Okay.
so much, Sean.
You.
Please try and catch them for further questions. And we'll be back in a couple of minutes.